ஆமா போனதா ஐயா சாப்பிட்டு நான் எதுக்குனாலும் காரையும் கேட்க மாட்டேங்குது
I will do it. Let's see if the speaker has joined. Participants, so we have around 71 participants right now. So, hello everyone. So, the speaker, we are still waiting for the speaker today, Professor Amlan. So, he said that last time I spoke to him, he said, I'm joining in 10 minutes. So, it's almost 10 minutes now. So, we are expecting him anytime. In the meantime, I'd like to share with you some information that we are organizing a workshop in IEEE ANTS. So ANTS is a premier flagship conference in the domain of communications and signal processing, and this time it is being held in IIIT Delhi. It's being held in IIIT Delhi, and so I'm one of the organizers. So if you, so we will be sharing the call for paper for the workshop soon, and if you have any paper, please feel free to submit your work. Okay. Soon you will be, so you'll also see the call for papers under the workshop category in the ANTS official website, IEEE ANTS official website. So how was the session till now for the last 2 days? Any feedback? Of course, you all have given your feedback in the feedback form, but since we are still waiting for a speaker, so we have some time to talk. So we can have a one-on-one discussion till then. If you have any queries, you can give your feedback, but also if you have any queries or stuff that we want to discuss, as I said, I work on in the domain of machine learning, signal processing, quantum communications, and so I have been in IIIT for the past 6 years. Before that, I was in the University of Edinburgh for almost 8 years. So during this time, I have been actively involved in European standardization also for 5G communications, and right now I'm working towards not only implementation but also for standardization of 6G. So if you have any doubts, ideas that you would like to share or discuss with me, we can because we don't get much time between the talks. So since our speaker is late, so we can have some discussions like that. Anyone, if you want to discuss anything with me, please feel free.
It was very well explained, sir. We are able to catch them, but little fast, I feel. But it was good. It supports us in many areas. As a research scholar, we are able to, like LLMs, LSTMs, these things go around in my subject also. So I feel this FTP helps me in doing my research progress.
Great.
Thank you, sir.
Great. Of course, means yeah, I can understand totally that some of the topics that they will cover will go a little fast because it's a 7-day program, right? So of course, if it was a 1-month program or more, that would have been better. But 7-day program topics will go very fast, right?
Yes,
so
yes.
What my suggestion is to you is that means we as human beings, we won't be able to capture each and everything that we hear. Okay. So
we need to dig the topics.
Exactly.
So we need to explore ourselves.
Exactly. So whichever
Like
thing you
majority
like the
of the
most,
subjects.
yeah, whichever thing you like the most, or whichever thing catches your ear, so you just dig more into it. So this is also a time and the scope. There's also a scope to do networking among yourselves and with us. So everyone, the speakers, us as the organizers, you as the participants, we can all later also we can stay in touch and try to solve some problem together also, right?
Yeah, sir. Hope so.
Yeah,
Hope so.
great. So you are a research scholar or a faculty?
Faculty and research scholar, sir. Research scholar.
Okay. So you're pursuing your PhD.
PhD in computer science, sir, from computer
Okay,
science background, and
okay.
that is the reason also maybe I feel little like most of the things are based on communications and so okay, I could catch as it
Yeah.
is AI
Yes,
related.
see, the thing is that means even the computer science and communications, electronics,
Interrelated.
in today's world, they are very interlinked. Okay,
Yes.
so they're all interlinked in today's
That's
world,
why
and
I opted, sir. That is the reason I opted the course.
exactly. Good. Because a electronics student or a electronics scholar cannot say that I don't want to know about computer science and vice versa. Because
Yeah,
everything is application, everything is interlinked. Means even if you do a program, do a code, it has to go into some application. So if you don't know that application, then your
on what we can
code
work.
is of no use, right? So
Yes,
that's why those two verticals are very intertwined. So it's better to know each other well, right?
that's the reason. Yes, exactly, sir. Thank you.
Good. Hopefully our speaker will join soon. So we are already 40 minutes late. But anyway, one good thing is that he's going to take both the sessions, so he can stretch it. He can stretch a bit. He can stretch. He
Okay.
said he will stretch it a bit, and he's going to continuously take the session.
Thank you.
Yeah. Anyone else would like to share any feedback or would like to talk to us? Tell us about yourself. Everyone is silent. Anyone else? Okay, our speaker has joined.
Hi, sorry. Yeah, sorry for my delay. I just
No problem,
I got
Aman
a bit
sir.
late from my due to traffic to my
Oh,
home.
I can understand Kolkata traffic is
Yeah, before
not
talking
very.
holidays, right? You can understand. Yeah.
Yeah, and just before Durga Puja, it's pretty
Right.
bad.
It's pretty bad. Yeah, sure. Yeah.
Anyway, so participants, so I'll just introduce today's speaker to you. So we have Professor Omlan K. Chaudhary. He is a professor and the director of A.K. Chaudhary School of Information Technology at the University of Calcutta and adjunct professor of IIIT Delhi. He's also the former Dean, Faculty of Engineering and Technology of his university from 2016 to 2019. And a brief about his education, he completed his MTech from the University of Calcutta in 2001, and he also completed his PhD from the same university in association with ISI Kolkata in 2010. So he was a postdoctoral fellow after that at the School of Engineering in Princeton, USA, from 2011 to 2012, and he has almost 20 years of experience in engineering education and research. He received several awards. Among them, he received the DST Boys Cast Fellowship Award in Engineering Sciences in 2011. Then from Indian National Science Academy as a visiting faculty fellowship in 2014. Then the JSPS Invitation Research Award in 2016. Then a very prestigious Erasmus Mundus Leaders Award in 2017, among many others. He was also a visiting professor. He also received the Hamite visiting professorship from University of Cambridge in the UK. and also the Shiksha Ratna Award by the Department of Higher Education, Government of West Bengal, and IBM Quantum Research Access Award in 2021. So apart from this, he is an associate editor of Elsevier's Journal of Computers and Electrical Engineering, series editor of Springer Transactions on Computer Systems and Networks, and series editor of Springer book series on modern informatics, and guest editor of Springer Journal of Applied Sciences. He is a senior member of IEEE and ACM, a distinguished visitor of IEEE Computer Society, distinguished speaker of ACM, Vice President of Data Science Society, and Vice Chairman of CSI Kolkata chapter. His areas of research are machine learning, computer vision, reconfigurable computing, cyber-physical systems, VLSI CAD, and quantum computing. So he has enormous experience and vast, and he's going to enlighten us with a bit of that. So we as participants, we are delighted to have you, sir. So one thing, sir, before I hand over the mic to you, so you have 2 sessions today. We have 2 sessions today. So in between, I will not interrupt you. You plan your sessions as per your convenience. So I'll ping you again.
இப்ப நம்ம என்ன பேசுறோமோ அதுவாக தான் நமக்கு பாசிட்டிவா பாசிட்டிவா
Sure. I will, thanks, Professor Sudeep, and thanks to IIIT Guwahati and all the organizers, faculty members of IIIT Guwahati. It's very close to me. I have visited the institute that's I think a few months ago, and I met all the faculty members and I love the institute. And thanks for organizing this this workshop on a very beautiful topic, that is quantum communication and the advancements in quantum communication. So what I will discuss today, as is being said, that I will be discussing on the 2 topics. Okay. So topic 1 will be very fundamentals of quantum communication, and topic 2 we will discuss about this multi-party QKD, the device-independent QKD, right? And then we will discuss about quantum repeaters, and then we'll discuss about quantum blockchain and the advanced topics. So first one will be basic quantum communication, and then we will go to some of the advanced techniques. Okay. So what I will do, I will try to give a pause. So suppose I start from here and end at around 7:30. Okay, which is almost that means almost 1 hour. Okay. So what I will do, I will try to give a pause. Maybe I will give one pause in between, and then I will again give a pause at the end. Okay. So in between, when I will tell that you can ask questions, you can switch on your microphone, right, and ask your questions. All in the meantime, you can also put in queries in the chat box. Okay, right, and then obviously when I give a pause, I will open the chat box and I will try to answer those questions. Okay. So let me start my first part of my lecture. Okay. I hope it will be interesting. The only thing in quantum, when I start delivering a lecture in quantum computing, I don't know that where all the participants are. Okay. So maybe assuming that you know the quantum computing, right? At least the basics of quantum computing, and only the quantum communication part will be discussed. I will skip some of my slides, which are which will discuss about the issue of the preliminaries of quantum computing. Okay, so let me start with something which is okay. So this is the first slide, okay, where I will try to see the power of quantum power in data communication, which will be basically the things of data communication. And then I will, in the second part, I will actually go to the quantum networks. Okay, so my slide is visible to all of you. Okay, I will try to switch off my video to reduce the bandwidth, maybe, so that my slide is better visible. Let me just do this. Let me just do this. Okay. Hold on. Yeah. So let me just switch off my video, right? Okay. Just let me know that if my slide is visible to all of you. Can any one of you tell that yes, sir?
Yes, it's visible.
Okay, great. Okay. So I'm just skipping the initial stuff. I will shift for your study. So now here we will here we get into this. Look at the point of quantum communication. Obviously, when you look into the quantum as a quantum computing as a new paradigm in my computing, obviously it has to do something greater, right? Then only we will try to look into this paradigm and try to do more in the paradigm. So if we look into this, the things what quantum computing can do better is obviously the problems like searching, big data, finding new molecules for materials or for drug design, machine learning on a large feature space, right? It can do, and there is also something on the quantum communication and quantum security, that means and cryptography. Okay, so these are this power of quantum computing, the power of quantum systems or quantum machines will try to see its power in actually developing the efficient and secured communication. Okay. So we know that for a quantum system, we know that quantum is basically an in-memory computing where the qubits state gets evolved, right? And with that, the computing happens. And so the best technologies are trapped ions or superconducting qubits, which are really going great, right? But when you look into the quantum communication, obviously the most choiceable medium is a photon, because photon have also quantum properties, Photon polarization states are discrete, and we can have all the things like entanglement, superposition, and interference using the photons, and that's why. And as we are doing communication, where the optical fiber is one of the good medium, photon is chosen as the technology for quantum communication, both for guided quantum communication as well as for free space quantum communication. But I will not discuss much about free space communication in this particular discussion. We will come to maybe in a later time. Okay. So let us look into this quantum cryptography system. Okay. So what is a cryptography system? What is a cryptography system? We know the cryptography system is something where we try to have a sender and a receiver, a sender and recipient. And what we try to do, we try to make the data generated by the sender going through a public channel, right? And for that, we know that, we can use several techniques, like a technique like symmetric cryptography, where we have a single key, or a technique like public key cryptography, which uses a public key for encryption. Sender uses the public key of the recipient for encryption, and recipient uses the private key of itself for decrypting that. Now, obviously, in this particular domain, in the case of private key and in case of asymmetric key cryptography, where we have a private and public key, the cryptography is very complex. But the advantage of asymmetric cryptography is that we don't require a key exchange. But if we look into the symmetric key cryptography, where we can actually have a key which is shared between both sender and receiver, that is very simple, because we use the same key at the sender side for encryption, and we use the same key for decryption, It's called symmetric cryptography when the same key is used. But the challenge of symmetric cryptography is that we have to find a very secure public channel, because we are exchanging the key between the two, one sender and one receiver, and we cannot have a dedicated channel between each sender and each receiver, and then it will be a huge cost, and it will be and it will not possible to do that, right? So obviously there are algorithms in classical where we can exchange the keys, okay, but they are all compromised. They all can be compromised, okay, provided we think that there are computing powers, and why not quantum computers will be there, okay? We have seen that the RSA protocol can be cracked, okay, by the Shor's algorithm. So we can have a powerful computer which can do that. And the most important part is that, okay, we don't have a public channel, okay, to share the secret key. Now, quantum computing does a very uses a very important phenomenon, the choices of basis, and that's where we can do a foolproof sharing of the keys between the sender and recipient, and assuming there is an eavesdropper, still it works fine. Okay, and that's the beauty of the quantum key distribution protocol. Okay, so let's look into this. Okay, when we try to do this, okay, what is the key generation process? In a key generation process, we know that the key in the case of a normal classical cryptography is a random key. Okay, because why it is a random key? Because the key should be random, because we cannot, that means, okay, its probability of prediction will be pretty almost zero. That means we cannot probable the next element of the key, the next value in my key, right? And to do that, we require to generate the random, okay? Random numbers. So random numbers are used as a seed for the key generation. Okay, here also quantum plays a good role, right? Though I'm getting into QKD, but before getting into QKD, I'm trying to tell that what are the different opportunities this quantum randomness gives, right? I don't know what that means. I hope that that means you have understand the quantum states. But okay, right? If you look into the quantum states, right? If it was a single quantum state, a single qubit state, we know that what is the random here? The random here is the probability of a single qubit get measured as 0 or get measured as 1. This is completely probabilistic because the single qubit state psi is represented as alpha 0 and beta 1, right? And this alpha and beta, okay, if you keep the qubit undisturbed in the environment, in its own environment, we will also see that there is a Hamiltonian function which changes the state of the qubit system, and the alpha beta value goes on changing. And this right, and this is the randomness what is there in a quantum system, right? And that is inherent and that can be also be utilized as a key generator. Okay, that means we can always take a quantum source which will always generate just in its evolution will generate a sequence of alpha beta, and then if you go for multi-qubit, then there's a tensor of multiple alpha beta which are changing randomly, and so the entire distribution, okay, of 2 to the power n basis states are changing randomly, and that is where the quantum random number generator is. I'm just describing this because we will see that there is some application of quantum random number generator which we have recently done. Okay, I will come to that later, but let's see the QKD. Okay, so the quantum cryptography has 2 parts. Okay, one part is that using quantum technique for cryptography, okay, which is one of the technique is the okay, quantum key distribution. The other thing is for teleportation, by which we can do secure communication. Okay, using the quantum mechanical systems. Okay, the other part of quantum cryptography is basically called a post-quantum cryptography, in the sense that we need to develop cryptography algorithms with a resilient to quantum systems, And for that, when we come up with a new cryptography algorithm, we have to prove that this is resilient from quantum attack. Okay, we will discuss something on that in the next part of my lecture. Okay. So before going into the details of QKD, we have to understand two more again important things. Okay. One important thing is called the no non-cloning theorem, which means that you cannot have an unknown quantum state copied. What does it mean? I said that A psi equals to alpha 0 plus beta 1. So you don't have any operation which starts with a single alpha 0 plus beta 1 in one qubit, and maybe other qubit is initialized to 0. And then after the operation, 0 or 1 state of qubit, right? And after the operation, in the both the qubit state will be same value, means both the qubit state will be alpha 0 plus beta 1, okay, remains in both the qubit. There is no quantum operation which is possible. Though you can say that, sir, I can always transfer a 0 or transfer I can always make a qubit 0 and a 1. But when you make a qubit 0 and a 1, you have to understand it's not an unknown quantum state, right? An unknown quantum state is something which is okay, well, alpha and beta are known, and you cannot know alpha and beta unless you measure the system. And once you measure the system, either you get the alpha or you get the beta. Okay, so that's the way how you cannot know both the alpha and beta of psi, okay, by any way, and that's why no cloning. Another one is quantum entanglement, which we will see in one type of the QKD. Okay, one type of the QKD we will see where the entanglement is used, and entanglement is a very, very common phenomenon in the quantum system, which means that there are states which are very tightly coupled, and the coupling is so strong that if we divide it, if it's multi-qubit entanglement, if we separate the qubits, still the correlation between the qubits remain. And when we measure one qubit, okay, the value of the other qubit can automatically state it. Okay, and that's the quantum entanglement. We will use all these recipes in our quantum communication, and we'll try to do it. Okay. So let's see the QKD, which is the first most important discussion we will start here. Okay. So the QKD starts with something like this. Okay, QKD can be non-entangled, can be entangled. Okay. Okay. So the main focus of QKD is that, okay, you have one sender, one receiver, and we will share the key between them. Okay. And if there is an eavesdropper, or if there is untrusted, we will immediately get the information that there's an untrusted party which is trying to enter the communication or trying to disturb the communication. And that is very important. Okay. In a classical cryptography, attack scenarios cannot be detected immediately. There are some continuous mechanisms which is being acted upon to detect that whether any attack has happened or not. But there is no system, no logical system by which whenever attack is done, there is some disruption in the system and we can detect it immediately. Such is not available in classical system, but that is available in the quantum system. We'll see how it happens in quantum key distribution. Okay. To understand the quantum key distribution, the first level, which is not the entangled bits, which is the polarization based. Okay. We have to understand that the polarization of the photon is a principle by which we actually do it by means of the polarizing filters, okay, which actually is something which actually changes the orientation of the photon. Okay, and then there are two things. There is if we see this particular picture, okay, let us try to look into this particular picture, what it tells. Some of you can understand. This also tells that there are two bases of measurements. In one basis of measurement, okay, horizontal polarization is 0. Sorry, vertical polarization is 0, equivalent to a 0 state. The horizontal polarization is equivalent to 1 state. In another basis, plus 45 degree orientation is a 0 state, and minus 45 degree orientation is the 1 state, right? And these are called vertical horizontal basis, and these are called diagonal basis. I hope this is okay, right? And these bases are important, or these orientations of the photons are important to understand that what value we are trying to send to the photon, okay? Why? Because if you are trying to measure a photon orientation across 0, okay, suppose we try to, okay, suppose let us just try to little bit more fundamental, okay? Let us try to assume that this is the photon state, and I am measuring this photon state across this basis. This photon state across this basis will be not 0 or 1, but it will be root over, it will be 0 plus 1 divided by root over 2. This basis will be, and this state, okay, this state across this basis will be 0 minus 1 by root 2. Similarly, but if you are measuring this in this basis, with this basis, there will be 0 and this will be 1. So this is the difference between the polarization, measurement, and the basis. So if we change the basis, the value of the same polarized photon will be different. And this is the catch, what is used in the one version, the simplest version of the QKD. Okay, so we look into this here. So to understand which basis my photon is, I can use two filters. The first two filters are the filters for the horizontal and vertical and horizontal basis. And the second two filters, this and this, are the filters for the diagonal basis. Now you see what happens, okay? So if this particular state, okay, this particular state has been taken by this, so see, that means this particular state is a diagonal state, but I am using a vertical horizontal filter, right? And then the state will not be properly taken care of, okay? Vis-a-vis, if I take a state, okay, which is like this, right? And we try to measure with a diagonal, then I will have a different result. Okay? See, the results are only matching when, why? Because this was your input state, this was the output state of the filter. This was your input state, this was the output state of the filter. This is the input, this is the output, this is the input, this is the output. This all input and output are same because we have used the proper filters for all the states. Here, inputs and outputs are different because we have used different filters for different We have chosen wrong filters for the different polarizations. And so these will have high error. So wrong filter applied will have a very high error in measurement. Okay? And that's the catch which is being used in QKD. Okay? So the quantum key distribution protocol, if you try to look into this, is simply like this. We have an Alice and a Bob. Alice sends a photon, either 0 or 1, using a random choice of rectilinear or diagonal polarization filters. So rectilinear, what we discussed as horizontal vertical, is rectilinear, and diagonal is diagonal. So we pass the 0 and 1, but the bases are random. Okay, maybe 1, 0 is on the rectilinear basis, maybe the second one is on the diagonal basis. Okay. Now, what happened? This is the full shown scheme. Okay. So you see that this is obviously we said that's how we'll do that. So for the best source for this is a single photon laser. Means a laser which emits single photon in every instance, and we polarize the photon, each photon independently. This is doable, but this is a bit costly. But I'm not getting into the instrumentation part of this in this lecture. Okay, we assume that single photon is available. And provided single photon is available, then what Alice does, Alice randomly changes the basis. Now what Bob will do? Obviously, this sequence of photons, why Alice is sending to Bob? Because through this sequence of photons, Alice is trying to communicate a particular key to Bob. Okay? So now to know this, know the string of each photon carries, you can assume each photonic state carries 1 bit of the key. So number of photonic states is the number of keys that Alice is generating, length of the key that Alice is generating. But there's one catch. We are sending the photons, but the bases of the photons are randomly oriented by Alice. And now what Bob can do? Bob doesn't know what are the choices of bases that Alice sent. But Bob can again randomly orient its filter. The filter options are 2 filter options. One is a rectilinear filter and one is a diagonal filter. Now the logic is that if Bob aligns the filter properly as that of the photon basis, correctly as that of the photon basis, then Bob will get a high value. But if Bob cannot orient the filter according to the basis of photon, Bob will get a very low value. So what do we see that, okay, Alice, try to look into these 4 sequences, okay? Try to look at this was the Alice value, 0, 0, 1, 0, 1, 0, 1, 1, 1. And this was the choice of filter of Alice, which means that if we just look into those, it means that Alice has sent the value 0 using the diagonal basis. Then 0 rectilinear basis, then 1 diagonal, then 0 rectilinear, then 1 diagonal, then 0 diagonal, then 1 diagonal, then 1 diagonal, and then 1 rectilinear. These are the choice of basis of Alice. Now, Bob will not exactly know the randoms. So one important thing here is that, what is the randomness here? Randomness here is the choice of basis of Alice. It's pretty random. Now, suppose I assume that, obvious, not assume, Bob will not able to know this random choice of basis of Alice, okay? Bob will try to do in his own way. So we will see that in some of the cases, Bob's filter, okay, will match Alice polarization. For example, remember the first bit. if Bob's polarizer failed, Bob's filter failed because Bob has used a linear filter, whereas Alice used the diagonal basis. So the interpretation of the Bob will be different. Okay? Right? Actually, what will happen is this particular values, when they are not, when the filter of Bob is not oriented with the Alice, Bob will get a very low value also. Though I can tell it is 1, but the value measured, okay, the amplitude of this state will be pretty low because the orientation of Bob's filter, Alice basis is completely different, okay? But in some of the cases, like the second case, Bob's orientation and Alice basis, Bob's filter and Alice basis are mapped. Both are linear. So here they will get the exact value. So wherever Alice filter schemes and Bob's schemes, okay, Bob schemes match, then they will get a good value. Where not, they will get a very low value, okay? So now let us try to see that what happens if Eve comes in the channel, okay? So if Eve comes in the channel, it will try to measure this, okay? And once Eve will try to measure this, it will distort this channel. And once you distort the channel, Bob will get all the bits after that with a very high error. And Bob will understand that there is an attack. And Bob will also inform the Alice, maybe to a public channel, hey, we are attacked, there is an Eve, so get out, okay? So then Alice and Bob can stop this communication. So the plus point of it is that as soon as Eve tries to read the channel, okay, the state becomes noisy due to decoherence. And that's what is there, okay? Now what happens is that, now how the key is ultimately settled. So key is ultimately settled by a public communication between Bob and Alice. So what Bob tells, that, hey Alice, I have got your bit 2, bit 5, bit 8, bit 12, bit 13, and bit 15 pretty well. All ours were pretty noisy. Okay? Then Alice will tell Bob, hey, hold on. So the bits where you got the values correct, where you got the values high with a low error, use only those filters in sequence. And Alice will also then know that, okay, these are the orientations for which Bob can orient perfectly. And then Alice will decide on those sequence, and that is the key. Alice and Bob will decide that particular sequence of photons for which, okay, Bob has correctly oriented the filter. So what happens is that if you see here, okay, out of this string of bits, okay, here, and here, Bob and Alice filters are, Bob's Alice orientation and Bob's filter are perfectly oriented. So now they decide that, hey, this string, instead of the entire string, 0, 1, 0, 1 is the key between the Alice and Bob. Okay, now there are two things here. That what is the difference between error in a eavesdrop, attack, and what is the difference between the error when Bob doesn't orient his filter as per Alice? So the two, though both are errors, but in case of once eavesdrop occurs, a sequence of error with long sequence of error will happen. So then Bob knows that this is due to the eavesdropper. But in the case of non-orientation, in case of non-orientation of Bob's filter compared to Alice, okay, as it is both are random, so there will not be a sequence of long error, okay? Only a small sequence of error. Maybe two polarization photons it cannot measure. Again, it measures a good photon. So then Bob will know that, hey, this is there, okay? Just hold on. Hello? Hello? Uh-huh. Uh-huh. একটু পরে ফোন করবেন না? হ্যাঁ, বলুন। হ্যাঁ, না মানে অ্যাপ্লাই করেছিলাম দুটো, হ্যাঁ অ্যাপ্লাই করেছি। হ্যাঁ 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 অনেক দিন আগে, 2 মাস। আচ্ছা, ঠিক আছে ঠিক আছে। ঠিক আছে। না, আপডেটটা সেমই আপডেট আছে, ঠিক আছে? আপডেটটা সেমই আছে, মানে সেম আপডেটই আছে, মানে সেম অ্যাড্রেসই আপডেট আছে, ঠিক আছে? হ্যাঁ 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 আমরা আপডেটটা পাই না, আমাদের কাছে আসুন আপডেটটা, ঠিক আছে? হ্যাঁ হ্যাঁ ওকে। Oh, sorry, there was actually phone from Aadhaar, that's right. Sorry. Okay, so okay, so this is okay. So now, okay, this is the scheme. So I will explain the scheme. You can go through. You will find. So I will just stop a bit. Okay. If there is any questions up to this, I will just stop a bit because I'm just the midway my lecture. Okay. So let me stop this and then I come back to you. Okay. So tell me if there is any question. Tell me if there is any question, please. I can take 2 questions and I will again come back at the end. Any questions from any one of you?
Sir, good evening, sir.
Yeah, good evening. Tell me. Yeah.
Sir, in this key distribution, quantum key distribution, the advantage is that wherever any eavesdropping occurs, it will be detected at
Number one. Number two is that you can use a public quantum channel and a public classical channel to share the key, because you require a quantum channel and a classical channel also. Because in the classical channel, if we'll communicate with Alice and tell that, okay, these are the sequences where I got the value good, so that Alice know that what are the exact sequence of the code which they have to share as a key. So 2 things. One is that you can use the public, both quantum public can be done, because if somebody wants to, as you rightly said, if somebody wants to attack that, immediate information will be there, immediately sequence of error will be there, right? And you can share it in a public channel. So there are 2 advantages. One is that you can share it in a public channel,
Okay,
and second is that you can actually you can actually do it, you share on the public channel, and you can actually that will detect whether there is any attack. Yes.
Okay, sir. Sir,
Yeah.
and one more question, sir.
Please go ahead. Yeah.
That is, depending upon the angle at which the photons have been communicated, we are representing that zeros and ones, right, sir?
Yeah, zeros and ones. Yeah. Zeros and ones. Yeah.
Sir, this is similar to that of the bits which have been communicated, like in terms of networks, like if you are passing the light, it will represent a 1 bit, and if you are not passing it, it is a 0. Similar to that, sir?
It is, yeah, that means see what happens is that 0 and 1 is also a measured data here, right? Okay, so polarization is actually something which means that what is the orientation of the photon vector. Okay.
Okay.
So if we consider photon as a vector, it has an orientation. Means it is basically this orientation is across a field. Okay, whether the field associated with the photon is horizontal, vertical, diagonal, up diagonal, or negative diagonal. Okay. This is the field associated with the photon. Now this field is properly captured when we pass the filter, which is properly oriented with the photon polarization. And this field will be pretty weak if we have the polarization and the filter in a different orientation. Now the field will be strong always for 0 and 1. The difference is that, okay, a 0 vector will have a very high value across the vertical axis of the polarizer.
Okay.
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 Okay, right? And one can it can be vice versa. I'm just telling. And one can be very high value across the horizontal axis of the polarizer. So that is the value what I get of the field in different, but either 0 or either 1 I will get in this orientation of the filter. Okay.
Okay. So,
Yeah.
So filter, what sort of filter we might be using it for detecting that polarization, sir?
These are called gratings. Okay. And these gratings are very matched with the wavelengths of the photon. Okay. And so this is a sort of you can just try to find that photon is a particle, okay, whose field gets, okay, that means whose field gets maximized in. So that means it is a sort of filter where you can either pass in this direction, okay, right,
Okay,
or you can pass in this direction.
Okay, sir.
Got my point. So okay, so the filter, that means either it can go in this direction or it can go in this direction, which means it is a horizon, it's a vertical orientation, or it's a horizontal. And these are so fine that you can only, that means it is a some sort of, you can discuss both with wavelength as well as the particle property of light, but it is actually something like that. You can understand, okay?
Yes, sir.
Okay, yeah.
Thank you, sir. Thank you.
Okay. So, any more question? I will just answer one more question and get back to my discussion. Okay. If there are no questions, I will just try to finish up this, and I will try to discuss something more, which will be very much. So this part we discussed. Now we'll try to discuss that. Okay, let's skip this. I will come to this later, maybe. Okay, so this is the scheme. I will just stop this. Okay. But what we discussed is a very, very ideal state of quantum channel. Quantum channel can be noisy. Okay, that is we are telling that the noise in quantum channel, that is, we are telling that error will be in the quantum channel to wrong polarization, but it can also be due to the noises. One is the circuit noise, which is basically used for generating the polarized photon state, right? Or the channel noise, which is used, which is in the channel. So this can also come up, okay? So now this is I'm not getting into this. This is a study what we did. We had a funding funding for the MIT-QCAL project, right, which was supported by Ministry of IT. And there we were given the opportunity to work on the, obviously, free simulators are there, like the CASM, like the QSIM, what is given by CDAC. And we got the opportunity of the bracket, which was from AWS, okay, for which you require the credits to run on the physical machine. So we did some experiments using the different simulators, okay, QSIM from CDAC, CASM from the IBM, bracket from the QCAL project. We did some, this is the way how you can generate the circuits which can simulate this particular stuff, okay? Right, this is a sort of research which we tried to do and tried to see that what are the actual implications of the errors in the different hardwares, simulators and hardware, because all were not hardwares. QSIM and CASM were simulators, and AWS were actually hardware. Okay, so these are the things we did with collaboration with CDAC Bangalore team. Okay, this is a good way to look at just some of the publications we did it. Okay, now going ahead, we will take this up QKD as a particular, maybe in the physical layer of your quantum network, and we'll try to define a sort of a push it to the top layer, which is the AES or the encryption layer. So we will try to push the QKD plane and generate the keys, and this case will be used in the application layer encryption. And that is one of the good, one of the good package of the why I will require QKD. So QKD keys will be taken higher up and we use an application layer to encrypt. Okay. So this is one of the good things to do, and these are the physical things how you can do this QKD using the optical experimental setup. So I think on a national quantum mission, okay, some of the labs will be doing this. We'll be trying to generate this QKD source and QKD receiver, and from there we will have the APIs to collect the QKDs and use in our application programs. That is the research what we are doing now. We are not expert in photonics, obviously, but we have expertise in actually, that means studying or understanding the QKD protocol and quantum cryptography and other quantum key distributed protocols, and we're trying to develop the application platform, okay, which is almost ready, where we can use the QKDs generated by the different hardwares and can plug into our message passing protocols, emailing protocols, all these protocols, okay? And we're trying to test this over the platforms by IBM or the platforms of simulation platform of CDAC, okay? All this, okay? This is a group we have, right? Those who are interested to connect with us. This is the group we have. We have some more collaborations, but presently I'm only showing a collaboration that we did with HCL and CDAC. Okay, and this is a good work in which we did in HCL. We developed a quantum random number generator patented both in India and US. Okay, with HCL Technologies, where it's not QKD, but it's a QRNG, means it's a quantum random number generator. And the problem in quantum random number generator, is, hey, you can say that quantum states are random, but when we try to extract those quantum states, there is a noise. And due to the noise, though the quantum states are random, many of the quantum states is to be discarded because there are high noise. And then what we need to do, we need to generate the large key using a sequence of quantum random number generator and then concatenating them. And then that becomes a very messy thing, okay? Because you have to run your quantum hardware several times, okay? And we have to drop off some part and we have to add them and concatenate to make a larger key, which is a bit messy, okay? So we developed a sort of auto-correcting quantum state circuits, which means that there is a sort of then obviously we have used a sort of learning paradigm by which we can correct the errors generated in the quantum states and we are trying to maximize the length of the quantum random number generator as large as possible, so that we don't need to reiterate the quantum hardware, and we don't need to go into the concatenation. Okay, we can generate a larger chunk, and maybe a few concatenations will do the job. Okay, that was our called SERC, auto correcting reversible circuits, to reduce the error in the quantum random number generator. Okay, right. And the other thing what we do is that we trying to, that obviously the post quantum cryptography solutions, okay, they also generate on random number generators, right? And we try to not only use a quantum random number generator, but the same quantum random generator can be used for multiple parties. Okay, and this is called a quantum safe key exchange. And we also, this work is under research and going on, and soon we will try to publish this. Okay, so it's a safe key exchange, quantum safe key exchange between multiple parties. Okay, all these things we are doing, QKD, and this is a sort of a experimentally QKD is going on very well, right? You know, QKD in different Indian labs have already established the QKD successfully. International labs have already done. CERN was the first, I think, in 2009, 2000. So we have to remember that quantum communication, in terms of implementation, is far ahead than quantum computing, because quantum communication doesn't require so many qubits. Quantum computing requires a large number of qubits to get at least to do a breakthrough in terms of the size of the solution. But quantum communication is very good. But the quantum communication cost is high, because you need to have those polarizers, you need to have those photon sources, okay, single photon laser sources, right, detectors, receivers, which are costly in the quantum domain, and their alignment and all these things. But the scalability in terms of the number of and you will only use this for the key exchange or key communication. Okay, so that is very, very, very well deserved. Okay? So this is the thing what I want to say. This is a very fantastic group of researchers in quantum computing as a whole. We have started the quantum communication group, or looking to the development quantum internet rather. Okay, in the last 1.5 years. Okay, right, and this is the group which is doing, consisting of some of the researchers and the postdocs. Okay, so these are the references. So what I will give you now, I can come to again a question, and maybe I'm just ending this first part of the lecture. Okay, we'll go to the second part of the lecture maybe after a 15 minutes break. Before that, I can take maybe a couple of questions from you, if they are ready.
Participants, if you have any questions, please ask now.
Yeah. So you can also push into the, I think there is something in the chat box. Is there anything in the chat box?
Yeah, so a person asks, so the live chat is on, so he's asked, Hafiz is asking, can't we share symmetric key using public cryptography?
Yeah, public cryptography is obviously that means okay, you will not require this sharing, because in the case of public cryptography, you encrypt with the public key of the receiver, and the receiver decrypts it with their own private key, and private key need not to be sent. But as I said, a public private asymmetric cryptography is a costly affair. So somehow if you can have a shared key communication, but where the key is not disclosed, key cannot be disclosed between any third party. That's the best easy communication, and for that QKD helps. You can share a key in a public channel, using a public channel, and you can share the key between the two parties. And if there is any eavesdropping, immediately you can know what is happening, and you can just get out of this key sharing. So that's why the QKD helps. Okay?
Any other questions?
I'm not getting the chat box, right? I don't know why I'm not getting. Can I view the chat box? No,
No, sir. There is some issue with the chat box, but there is a real-time live chat. That should be below your.
Okay, then you can take the chat. I can answer. No issues.
Yeah. So any other questions?
So if there are no questions, give me 10 minutes break. I will not extend to 30 minutes. Maybe we will join around 7:50. Is this okay?
Yeah, sir, that's fine.
7:50. Just
we have one more question, sir.
One more question. Yeah. Please go ahead. Please go ahead.
Yeah, please type as a crypto analyst. Yeah, please type. What are the ways? Just a moment, sir. He's typing.
Sure.
So he's asking, as a crypto analyst, what are the ways of attacks? This is his question. What are the different forms of attacks? He wants to know.
This I will discuss in my next discussion. There are side channels. So side channel is just something we always say in terms of the attacks. Okay, but one thing in that QKD we will very soon understand that in the other part of QKD also, if there is an untrusted device also, QKD still works. We will discuss the entanglement based QKD, where if the entanglement measure device is untrusted, still it works. So that's called a device independent QKD, which I will come. Okay. Here the problem is that one issue in scenarios of attack in the Alice and Bob is that if the Bob is attacked, okay, that means if somebody tries to sneak through what Bob is doing, right, then probably your key is revealed. You cannot do it in the channel. But if Bob is compromised, if it knows that what are the exact filters Bob has applied, and then the public channel Alice and Bob communicates that okay, first filter is okay, fourth filter is okay, seventh filter is okay, 10th filter is okay, 9th is okay. Then if somebody sits on Bob and also hears the public channel, then it is compromised. Though it is not compromised from the channel, but it is compromised if the Bob is compromised. The key is compromised. But we will see another technique where we will find that there is another different way of the QKD using Bell state measurement. Then if the Bell state measurer is the compromise also, it will not be a problem. Because here the orientation of the filter is a sort of measurement, and their compromise can happen, and their QKD can fail. Okay, this is one of the attack scenarios. Other attack scenarios we are studying that if there is a high amount of side channel which can change the basis in the channel itself, or can produce high noise in the channel, and that is intermittent, not continuous, then Bob can get confused whether it is due to the channel or whether due to the wrong position of the filter. And then Bob can actually come with a very short value of the key, which is very much, which is predictable. And that also makes the QKD vulnerable. Okay, so am I clear to the answer? Are you clear with my answers?
I think he says yes.
Okay, great. So let's give a 9 minutes break, okay? And then come back at 9 to 10. I'm keeping all the things on. Only I will just switch up my camera and microphone. We'll join at 19:15, okay? 7:50, huh? Okay, okay, bye, bye. Yeah, okay, so can we start now, the next part of the lecture? Are you all okay? Because I want to squeeze it back from 9, huh? That's right. Okay, can I start? All of you?
Yes, sir, please start. Yes,
Okay, great. Sure. Thank you. Let me switch off the camera and start the presentation. Huh? Okay, so let me go back to the second lecture. Let me go back here. Okay, so I will now go to a little bit advanced topics. Okay, so we discussed. I think the my slide presentation is visible, right?
Yes, sir.
Oh, great. Okay. So this is the second part of the lecture. Why in the first part we knew about fundamentals of what are these quantum photonic states and how we can use the polarizers, what are the different bases we can use, and how QKD works, and also there's some good discussions on what are the ways they can be some sort of the attack scenarios. Okay, so we had a fundamental of the quantum communication, data communication done. Okay, now we'll go to the next level, and as we see that the motivation is that this is also one of the research motivations what we are trying to look forward, that how we can that means define that is our computer networks, and how we can take the best uses of quantum communication in our present computer networks, and so it makes the future generation quantum, future generation networks, okay, utilizing quantum. Okay, so this is a brief content. I will just try to make it short. Okay, I will not make so much elaborate. Okay, so let's I will just skip a bit. Okay, so this is. From here we should start, because this particular lecture will involve a lot of things regarding quantum entanglement. Okay, so if you look into this quantum entanglement, okay, this is a multi-qubit phenomenon, and they're highly correlated. There are circuits which can do this. Okay, I'm not getting into the circuit here, but I'm more into the quantum states here. Okay, so if you look into the example state 5 plus, okay, you see that 5 plus is a 2-qubit state, but it consists of, the state vector consists of 2 states, one is 0, 0 and 1, 1, whereas a particular 2-qubit state, that means a generalized 2-qubit state, will have all the states like 0, 0, 0, 1, 1, 0, 1, 1. So this particular state, okay, is a disruptive state. Okay, is a disruptive state where we have, instead of the probabilities of all the possible basis states in 2 qubits, we have only the 50% probability of getting measured as 0, 0, and 50% of getting measured as 1, 1, and no other state. And the other, this is a disruptive distribution. So, okay, so the generic distribution of 2 qubit is that all the states will have equal probability. Means 0, 0 will be 1 by 4, 0, 1 will be 1 by 4. Okay, then 1, 0 will be about 1 by 4, and then 1, 1 will be 1 by 4. Okay, because it is 1 by 2 to the power n. Okay, n minus 1, okay? But here we have probabilities of 0, 1 and 1, 0 not existing. This is one thing, okay? This is after distribution. The second part is that you cannot partition the 5 plus state into two disjoint qubit states. You cannot write 0, 0, 0A, 0B plus 1A, 1B as 2 quantum states, as a tensor of 2 quantum states A and B. Means that they are so tightly coupled that you cannot make them bipartite. You cannot partition non-bipartite state. You cannot partition the 2 qubit state into 2 single qubit states. And this means these 2 qubits, though it's a 2 qubit state, but 2 qubits are so strongly coupled that you cannot partition them into 2 individual qubit states, okay? And though 5 plus is one of the entangled states, psi plus, psi minus, and phi minus are the other entangled states in the 2 qubit. The other good point of entanglement is that if you look into the 5 plus state, which is 0, 0 plus 1, 1, if we measure the first qubit can be 0 or first qubit can be 1, depending on, because this means that 50% probability of getting 0, 0, because probability is 1 by square, amplitude square. So amplitude is 1 by root 2. So square is half. So 50% probability of getting measured as 0, 0, and 50% of getting measured as 1, 1. Which means that if I take 2 measurements, one measurement will be 0, 0, and one measurement will be 1, 1. If I take 100 measurements, 50 measurements will be approximately 0, 0, and approximately 50 measurements will be 1, 1. Because there's like equal probability. But do we need to measure 2 qubits? Actually not. Because if you see the state, if I measure the first qubit 0, as their entanglement, I don't need to measure the second qubit, because the first qubit is 0, second qubit will be 0 because I will be falling on this state. Or if the first qubit is 1, then second qubit will be 1 because I'm falling on this state. And similarly, for the all other entangled states, either it is first and second qubit is same, or first and second qubit is a not. So which means that in any entangled state, if we know the first qubit, your second qubit may be same, or second qubit may be just a not of that. You have to know that which one you are doing, okay? That's all. Now, we will look into this quantum entanglement into two specific applications, which is related to quantum security. One is quantum key distribution, and one is quantum teleportation, okay? So, we have already discussed about discrete variable QKD, which is basically BB84, what we discussed, okay? There is something called continuous variable QKD, where it encodes something on the continuous variation of amplitude and phase, okay? But we will be mostly interested in entanglement. It will discuss mostly entanglement QKD and extending that for device independent measurement, device independent QKD, which is the most strongest QKD in the entanglement case, okay? So let's see what it is, okay? So this was your BB84, we are not discussing further, okay? There is entanglement based QKD. What happens in entanglement based QKD is that we generate the photons in Alice and Bob, okay? And we try to do a entanglement measure. And this entanglement measure will tell us that this entanglement measurement value will go to Alice and Bob, and Alice and Bob can understand what is the key they are exchanging. So without movement of the quantum states between Alice and Bob, using a measurement at an intermediate and getting the value of measurement will make them understand that what is the key they're exchanging, okay? So this is called BSM. So BSM is something that BSM is something called Bell state measurement. BSM is measurement. BSM is something which is called Bell state measurement, okay? And this Bell state measurement will give you will enable both the Alice and the Bob to actually understand the key, okay? Now, let's try to go back to this, okay? So how it is done, okay? So the way it is done is that Alice prepares basically the qubit photons, okay? And Bob also prepares the photons, okay? Then this Bell state measurement has an apparatus where the philosophy is that, I've not explained it in details, but okay, but the philosophy is that it tries to record those measurements. Try to listen it very, very carefully. Bell state measurement of the Charlie tries to measure those states for which Alice and Bob is perfectly coherent. Means, suppose there is a detector, Charlie. Charlie can detect those photons coming from Alice and Bob, which hits the measurement apparatus in Charlie at the same point of time and having opposite polarizations. Because the measurement equipment is such that one will go through the horizontal, means opposite, means it's not opposite polarization, opposite values in the same polarization basis. So what it does is that this Alice and so this Charlie records a hit when they find that Alice and Bob are hitting the measurement apparatus at the same time, and for Alice has made the 0 measurement maximum and Bob has made the 1 measurement maximum, or vice versa. Okay. Now, those measurements values at the Charlie are being pushed back to Alice and Bob. So Alice knows that on these measurement values, Alice and Bob have been measured with a very high value. Alice and Bob has been measured with a high value, and they are opposite to each other, because that's the measurement policy. So automatically Bob knows that what was Alice's key, and Alice knows what was Bob's key. Because suppose I know that okay, that means photons for me, which was maybe 1001, Alice also coincided, and in case of Alice it will be just opposite. So if I know what was my, then I can get Alice, and what was Alice? So Bob knows what is Alice, and Alice knows what is Bob, right? And then they can mutually twin with each other. Then Alice and Bob can just say that, hey, you keep and I follow, or Alice said, hey, I follow, you keep, and the thing is done, settled. Okay, but the question here arises that whether Charlie can break this, can know that what is happening, okay? Now the measurement apparatus in Charlie is such that it knows that Alice and Bob is is basically opposite, but it doesn't know that what is Alice and what is Bob. Okay, so that's why the Charlie cannot actually get the data, but only knows that Alice and Bob have different. That means one is 0 and one is 1. That they know, and then they don't know that what they decided, what Alice and Bob decided. Okay. So this is the way how entanglement, and this entanglement based key exchange is much stronger in terms of communication, because this can also be used as a repeater, because through this process Alice and Bob can know each other, what data Alice has and what data Bob has, without communicating, and Alice can regenerate the data what Bob has, or Bob can regenerate the data what Alice has through this Bell state measurement. And this is called Bell state because the way this works is that preparing a Bell state and measuring that, and based on that I can get that what is actually in the Alice and what is actually in the Bob. Okay, so this is a sort of thing, and then we can actually now we can look into different types of side channels which can also happen in the QKD, right? And this is basically due to the real systems are not ideal, and real systems can generate imperfections. Okay, so let's look into this. So these are some of the ways we can generate the imperfections in the channels, be for entanglement based QKDs or be for the discrete QKDs. The first one is the electromagnetic signals, because electromagnetic signals interacts with the optical photons, and the reflected signal from the photon can actually give some sort of idea that what was the state inside the channel. Though experiments are going on that whether they are completely undetected at the Bob's or Alice side if this attack occurs or not. Okay, but these are there. Okay, and imperfect lasers, single photon lasers are pretty costly. Many a times people uses a pseudo single photon laser, which by itself spreads up in the wavelength, okay, or in the nature of the particle. Instead of a single photon particle, it may be two photon particles which is going simultaneously, and then all imperfections works. Okay, and if the detector imperfections, okay, can also be coming up. Okay, and all sort of things can be happening, right? It is people are trying to look into the modulators, injected light, power analysis of the sender receiver, can they resolve something? So all these things are the side channel and the attack scenarios. Okay. Now there are different types of, so these are very, very good research domains. Okay. But the challenge is that to do this, you require the QKD sources and QKD receivers. Those who are interested, I think there are few initiatives in India, like we know the CDOT Delhi. I know the group which have developed the QKD transmitter receiver, the eavesdropper, and the channel impairment simulations you can do and you can get it. And I think the quantum computing lab, which is starting up as per in QM, right? If QKD is there in that lab, then you can try a lot of experiments on this. And there are a few companies, okay, who have also have their QKD sources, repeaters, and test bench, which can be explored. Okay. But in the simulation side, or the communication protocol development side, you have to develop the side channel noise models equivalent. So the good point is that the noise models in the quantum domain can be represented by some unitary matrices, which are the extra quantum transfers which generate quantum transformations which generate these noises, or some mixed matrices which are unitary and non-unitary combined. So non-unitary transformations of the quantum states are also noisy because they don't preserve the quantumness. So those are the ways we try to model the noisy channels and try to find that as we do in quantum circuits, the depth of the quantum circuit, the get depth of the quantum circuits, the error resilience of a quantum circuit. Similarly, we can find the resilience of those in terms of how many parties can communicate together, right? How many repeaters we can put in the links, right? That means we can also look into what are the timing synchronization required between the Charlie and the Alice and Bob in case of entanglement QKD. So all these things can be simulated and the scenarios can be developed, which obviously needs to be mapped with the physical experimentation on real QKD to get the exact metrics of these errors. Okay. Now we'll come to another. So I think, okay, QKD we have discussed the techniques and we have discussed some of the things which are in the real scenario, side channels and errors, and how to understand those. Okay. Now I come to the next important technique of quantum information transfer or quantum communication. And the beauty of this technique is that you transfer the quantum information. Try to listen to this very carefully. You transfer the quantum information using classical channel. So, having said this, I have hidden something, and that is, so you can tell me that, sir, how it is possible, right? The quantum information through a classical channel. It is possible because obviously I have kept one thing hidden, that it is not only a classical channel, it's a classical channel plus a Bell state generator which connects both the sender and the receiver. Okay? So what is the technique? The technique is very unique. And this is one of the best communication you can do. Errorless communication. Long distance teleportation, satellite communication. The cost is that you have to have the Bell-State generator connecting the sender and receiver, okay? So let's try to understand this in a very fundamental way, okay? I think the left part is something which is being there, okay? So there's a Bell-State generator, and we know what is a 5+ state, the most easy Bell state, right? 5+, 0, 0A and 0, 0, 0A, 0B plus 1A, 1B. Let's try to assume that this was the Bell-State generator, though we can do it for all the Bell-State generators. 5+, 5-, psi+, psi-, okay? Let us have a Bell-State generator, okay? Now this Bell-State generator generates the Bell state and then partitions the 2 qubits. So A goes to Alice and B goes to Bob. Okay. Now the activity to be done is that psi has a quantum state and Alice has a quantum state psi. Bob should receive that quantum state because this is communication. Alice should be able to transfer its quantum state psi to Bob. If it is done, then the communication happens. So let's see that how using the Bell state this communication happens. So what is actually done? Again, I come back. Bell state is generated. The 1 qubit is shared. 1 qubit goes to Alice. Maybe the A qubit. The B qubit goes to Bob. That's the only thing we have to do quantum. Okay. Then what is done? One operation is performed. Okay? Actually, it is the projection of psi on the Bell state. It's some sort of operation combining psi and this part of the entangled state. And this operation does a measurement. Okay? And this measurement generates 2 classical bits because one comes from phi and one comes from psi. And the beauty is that these classical bits, these classical measurements are communicated through a classical channel. Actual communication is not quantum channel. Actual communication is classical channel. So what Alice does, Alice sends classical information to the measurement value to Bob. And what Bob does another operation, he incorporates these measurement values, knowing these measurement values, and getting the partial entangled state, there is an operation by which Bob can regenerate psi. And that is the important thing in teleportation. So the summary of this problem is that using the partition Bell state, Alice does a measurement operation involving its partition Bell state and the quantum state psi, and that measurement data goes to Bob. Bob uses the measurement results from Alice and its share of the entangled state and can regenerate the value of psi. Okay? And that's what is quantum teleportation. And this quantum teleportation can help to communicate the data using the quantum data. Try to understand quantum data between two parties. using the classical channel and using a Bell-Stems generator. So if you want to communicate, if Alice wants to communicate the same information to more parties, then each of them will have to use another part of the entangled state. So we have to generate from 2-qubit entangled to 3-qubit entangled to 4-qubit entangled. And so that's why there is a need of larger multi-qubit entanglement in quantum communication, because larger multi-qubit entanglement can generate communication between multiple parties. Okay, I can just have a brief pause here if there is any question. I can stop here because I am in middle of the second presentation, so I can have a brief pause here. So let me come back. So anyone want to have any question here, please get back. Any question? Any question from anyone? Any doubts? Any?
No, sir.
So good evening, sir.
Yeah, can you little bit loud in the answer, in the question, yeah?
Sir, can you once again explain what are the different quantum protocols supporting communication, sir?
No, yeah, I will come to that in the next part. The next part of the campus, the next part of my lecture. But there are several. But what I am discussing here are the different 2KD protocols, and just now discussed about teleportation network, teleportation protocol. Okay. Yeah, but we will have some discussion on the quantum repeaters in the next part of my lecture.
Okay.
Okay. Anyone else?
Also, you will explain about all the key distribution.
Can you be a little bit loud? Yeah, please, can you be a little bit loud? Yes, please go ahead. Anyone, any question? Okay, so I think there is no question. So let me go back, huh?
Thank you, sir.
Okay. So now we come to the repeaters. Okay. So repeater is responsible for establishing long distance entangled with remote nodes, okay? Intermediate entangled pairs. So basically, what needs to be done? If you look here, okay, how we can make a long distance entanglement? Because long distance entanglement is required for communication. Just like teleportation, we discussed, right? So these quantum repeaters philosophically, okay, philosophically does this thing. What they do? They generate an entanglement, because this quantum repeater is closer to A, and B also. What is this doing? It will now generate a entangle between A and B. So what it does, it initially entangles this quantum repeater, generates entanglement pair between A and B independently. Generates an entanglement pair between node A and itself, and another entanglement pair between node B and itself. And then, okay, right, and then using this Bell state measurement, it generates an entanglement between A and B. And once the entanglement is established, it can just come out of this particular process, right? So how this is done? So what is done is that it uses a measurement technique by which it transfers the entanglement from here to here and from here to here, and so that these two are ultimately entangled. In a logical way, obviously, I'm telling you, right? Actually, there is a mathematical form of quantum measurement followed by state generation, by which we actually pass this entanglement from here to here, and then from here to here, and then we just isolate this quantum repeater from these two, okay? And these quantum repeaters are pretty important to generate the long distance communication. But again, the repeaters can have errors, and these are also how we can purify entanglement from noisy copies. So these are the very, very important research things which can be done, and people are trying to make this happening using the devices as well as protocols to make this happen for long distance. But theoretically, it is very, very good. So if we look into the fast generations, is basically low communication rate. Okay. Second is quantum error correction. Third is very, very high rate. Okay, multi-party. So these are basically the things, and these are basically the devices by which you can actually generate entanglement or entanglement creation between these two nodes. Okay? And quantum error correction, you know why, as I said, quantum error correction is something which means that the quantum state gets modified. And how a quantum state gets modified? A quantum state gets modified by some quantum transformation only. And if you accept that a quantum error is due to some operation of unwanted operation of U on the quantum state, you can understand what is the U by seeing the effect on some of the syndrome qubits. Then you can apply U inverse to uncom. This is a point in the quantum system. You can always uncompute. So if you know what is U, you can generate U inverse, and then you can actually make this psi back. Okay? And this repeated things can be done, okay? And there are entanglement purifications, quantum error corrections, all goes together. And then we can have something like remotely entangled qubits, teleportation, based error corrections, and all this. So this is a beautiful paper. You can look into the science, where it tells about the optimal architectures for long distance quantum communication. Okay. The other part of this quantum is that it's a post-quantum cryptography. So post-quantum cryptography is something that the people gets confused that what is this post-quantum cryptography? Because does it mean some cryptography after the quantum era? No, it's not like that. It means that it's a cryptography when we have full quantum systems working. When we have full quantum systems working, then it's called post-quantum, which means these are quantum resilient cryptography operations. And these are coming up very strongly. And there are groups which are working, and people are trying to use this in their servers, in their data centers, in their edge systems, because they know that if it happens, then if we don't do that, then somebody somewhere, some attacker has a quantum machine and it will break all the security. And actually we don't know that who has what power of quantum machine, because organizations are pretty secret about their quantum machines and quantum strength of the quantum machines. So now, instead of thinking that quantum machines will come up in the next few years very strong, let us think that they are there. Quantum machines are there already. And now if the quantum machines are there, is your cryptography safe? It's not safe. If quantum machines are there, your cryptography is safe if you are using post-quantum cryptography. It means that when the quantum is established. And there are different types of families, as we see, lattice-based, code-based, multivariate, hash-based, and isogeny-based. So there are different standards, niche standards, okay? Like we have the Dilithium, Falcon, Kyber. These are the very, very common suits which are lattice-based. Okay? And mathematical challenges are pretty different. And so the quantum computers, which are very good in doing the quantum Fourier transform, phase estimation, discrete logarithmic, those things will not work. You cannot decrypt using those techniques. And that's why it's called a quantum cryptography. Now, if we look into this is the research question, okay? So, what are the things we can do in the OSI or TCP/IP models? Okay. So, obviously, you cannot replace a classical function with a quantum function, because quantum functions like entanglement, no cloning, quantum swapping, these have no equivalence in classical. So you cannot tell that, hey, this was a classical thing and you want to make a quantum internet, so convert the classical into quantum. You cannot do that. So you have to think that how you can use the quantum techniques and which communication can be done. And communication will be different. But what is the advantage of that? So we need to also have classical. It's not that we will have entirely quantum, because quantum has certain limitations. Okay? So maybe some intermediate operations can be done in quantum, maybe in a more secured way. But long haul communications in quantum is still very risky because decoherence is there. So we have to use the quantum state and quantum transformations usefully, and we have to strengthen our internet protocols, and we have to make the internet protocols either enhancing security or in giving different or some new type of applications coming up if we develop these quantum protocols on this, okay? So if we look into this is some sort of visualization, and this was also published in a very latest survey 2024 in IEEE Communication Surveys and Tutorial, this work, okay? And this is the work you can look into, okay? So application transport network, link and physical. So there are different ways, right? And it can be a communication between quantum devices itself, which is very, very interesting, okay? Because quantum devices for quantum sensing, quantum devices for quantum computing, okay? These are the two strong areas of quantum systems. One is quantum computing and one is quantum sensing. And quantum computing itself will be now going to distributed quantum computing. And quantum sensing can be very large scale. So can we use quantum communication for those systems which are inherently quantum? Secondly is obviously quantum protocols and quantum service layers for the communication in the classical world, where quantum can achieve better security, maybe better safety, okay, like that, okay? And this paper is pretty important. You can look to this paper in 2024, published in 2024, okay? And this is a sort of visualization thought for that application layer encryption. Applications can be PQC, quantum algorithms, quantum MO. These are the true quantum applications. Though PQC is an encryption, quantum resilient encryption. Transport layer, where we try to make an end-to-end communication. So we saw teleportation can be end-to-end, right? It is basically makes an end-to-end. So can we use teleportation? Can we look into congestion control, quantum channel capacity? In network layer, we can use some sort of quantum repeaters, entanglement. I don't know what quantum network model something, but we are looking into some problem space where we have for large networks, we can define it as a graph, and maybe quantum algorithms for graphs can be utilized for different sorts of network analysis, large network analysis. And then in the link layer, it will be obviously some sort of, okay, quantum error correction, entanglement, okay? And physical layer can be different types of physical qubits, okay, which will hold the quantum state. So there are different the different layers of the computer systems and networks can be visualized or mapped in the various techniques of quantum, okay? Now I think I can stop here, right? I will just give some of the data which are there, okay? In terms of experimental theoretical values, quantum key distribution, presence status, okay? Quantum teleportation, presence status, all these are presence status. How much we have achieved. okay, quantum routing, multiplexing, what are different techniques of multiplexing, QC standards, something in the blockchain also. So blockchain, okay, we are trying to have quantum resistant logs, quantum, with a blockchain, quantum proof blockchain, the consensus algorithms for allocation and maybe resource scheduling due to entanglement. So these are the different things of the blockchain can be looked into in the quantum domain, quantum algorithms, and quantum security protocols can be checked in terms of blockchains. Okay. So I end up here. There's a lot of references you have for this discussion, and I end up here to tell that there are fascinating things which are possible. A lot of the things still are in the research level, except the QKD, multi-party QKD, teleportation, okay, long-haul teleportation, people are trying. QKD, people have used QKD for exchange of their keys for data centers. I have information from my industry friends. There are organizations which are giving you the QKD, physical QKD resources or through API to make your thing. Blockchain in quantum networks is also coming up in terms of can we use the entanglement in some sort of blockchain process? Can we use QKD in some sort of blockchain key communications? And these are the things which are being taken care and will be looking and will taken forward in the next immediate domain of research. Okay, so I stop here and let me get back to all of you for questions if there are any. Yeah. If there are any questions, please let me know.
Guys, if there are any question, please let us know. Any confusion or anything you want to ask, you can ask.
Thank you for the given information, sir. We are very much glad that we understood. Like we have learned many new things from you.
So, ma'am, if you can tell from where you are a faculty, researcher, or who you are, if you can introduce yourself.
Sir, I'm Santoshi, research scholars and faculty, sir, and even faculty.
In where you are?
I am in Matrushri Engineering College right now and scholar from SR University, Warangal.
Okay, good. So yeah, that means see the one difficult part in quantum is till now we don't have the quantum full-fledged labs in almost any of the institutes, right?
Yes.
But I think National Quantum Mission has given a real push to this. And I think we need to start working, thinking, developing courses. I think all of you know that the AICT book is coming up in quantum technology. So this is a level 1 book. More quantum books will be coming up for this, and we're very hopeful that this book will help a lot of the faculty members and researchers to get the quantum thing in a very formal way. Yeah, but the plus point is that research opportunity is enormous, and if you look into the way the government organizations and some of the top IT companies are progressing in the quantum, it's fantastic. It's the high time that researchers like us should try to come up with some sort of problems or solutions and try to catch them up and try to utilize their facility and to contribute. Yes.
Yes, sir.
Yes. Anyone else can have any questions?
Anyone have any
other
confusion?
chat box or something?
In chat, someone has asked that to ensure security, what requirements need to be provided in repeaters?
Oh, this is a good question. So quantum repeaters, as we see that they are at the Bell state transfers, they do, okay, for long haul, okay. Obviously, the issue here is that if we try to compromise the repeaters, what you can do, you can actually understand the Bell state of both the parties and try to have a guess of the teleportation going on. Okay. So in terms of protecting the repeaters, I think there will be some sort of random Bell state generators will be required so that they change the Bell state pretty often. If they are not inside the Bell state, but inside the repeater, but they are some way observing the doing certain measurements on the data generated by the Bell state generator. Okay. Other part can be that the Bell state. That means that there should be some means by which the two parties which are connected to the Bell state measurement. Okay, actually what happens is that the Bell state measurement in a true sense only knows the measurement value, but if we look into the teleportation, the actual value can only be generated if we know the part of the we know the part of this particular Bell state. Okay. In a case of only teleportation, if the Bell state generator is hacked, I think you are not there. You will be completely hacked. Okay. So if somebody compromises the Bell state generator as such, I think it will be a really catastrophic. But if somebody wants to capture the Bell state channel, then I think there will be some sort of error and some sort of thing that two other parties can connect and can just change the channel. But if the Bell state generator itself is compromised, I think it will be difficult. So that should be very, very secure. Yeah.
Anyone have any question? Anyone else? I think the silence indicates there is no more questions for this session.
Thank you.
Okay, sir. I am Shantan Das. We have already met before, and I am very lucky to hear you once again. I am PhD scholar under Dr. Sudeep Vishwas. On behalf of him, I would like to sincerely thank you for your valuable time and inspiring talk. And the topic is also so interesting and also useful for nowadays. It will really help us a lot to explore the new things, new way of communication and faster. Thanks you again for joining us, and spending so much time with us and help us to gather so much information. Thanks a lot, sir.
Yeah, thank you all. Thanks to the entire organizing team and all the participants, faculty members, researchers here. So I hope that we will physically meet sometime the entire context.
Thank you, sir.
Take care. Bye. Bye.
Okay, good night, sir.
Thank you. Bye. Thank you.
And thank you to all the participants. Also, please fill up the attendance form by 9:10 or 9:15. And we are and see you again tomorrow for the next session. All of you, till then, good night. Thank you.
Thank you, sir. Good night.
Thank you, sir. Thank you for the session. Thank you.